Question number 12, it reads, in a vessel is a liquid, density of which increases with depth y from its free surface according to this law, rho is equal to rho naught plus ky, where rho naught is a constant 1 gram per cc and k is 0.01 gram per centimeter per 4. Two balls connected with an inextensible thread of length 15 centimeter are dropped in this liquid. Volume of each ball is known to as 1 cc and their masses are as 1.2 gram and 1.4 gram. At what depth will these balls settle in equilibrium? So let's say this is the surface of the liquid goes downside, so from here y is being measured and these are the two balls. This is one ball, this is two. Lighter ball will be upside and heavier ball will be downside, and this length is 15 centimeter. Now if you draw the free body diagram of this entire system, that means the two balls consisting together, then you'll find this tension force is going to be internal force and external force will be the gravitational forces, that means weights acting downwards, and the buoyancy forces that will be acting upwards. So buoyancy force will be acting on this one upward as well as on this two upward. So we'll write the net force as m1g minus the buoyancy. M1g is downside and buoyancy is upside, so I'm writing downside as a positive, upside as a negative for 1, and similarly for 2 it's going to be m2g minus f2. This net force must be 0, so force balance at equilibrium, right? So it will give us m1 plus m2g must be equal to f1 plus f2. F1 and f2s are buoyancy forces acting on the ball 1 and 2 respectively. Now buoyancy force is submerged volume into the density into the gravity. Now since these sizes are very small, so we will say that this density at this location will be depending on this y, which is let's say y1, and this size is small, so it's not varying within. Okay, so it will be like buoyancy f1 is going to be the total volume submerged, which is v given to us, and the density at y1 depth, so we are considering this depth as a y1, and that density will become rho naught plus k y1, so it's a rho naught plus k y1 into g. That's first buoyancy. Buoyancy acting on the second is going to be again by the same formula, submerged volume v into the density at this location. Let's consider this depth is y2, so it will become rho naught plus k y2, the density, into gravity. So that becomes the expression. Now you can take gravity common and cancel, so it becomes m1 plus m2 is equal to v rho naught means 2v rho naught, and vky1 vky2, so we can take vk common, as this within bracket will be y1 plus y2. Now m1 is 1.2, m2 is 1.4, and v is 1, rho naught is 1, everything is in CGS, and this k is 0.01, so I have placed over here y1 plus y2. After simplification you'll find this will become 2.6 and this is 2 subtracting, so 0.6 divided by 0.01, which is basically 60, so y1 plus y2 came out to be 60. Then we know this y1 is up to this, y2 is up to second, so the difference of the two is the length, that means y2 minus y1 is 15 centimeter L. Now there are two equations we can handle. Once you add them together, then you'll find this will get cancelled out. Y2 plus y2 twice y2 is equal to 60 plus 15, that is 75. So y2 must be 75 by 2, that is 37.5. Similarly, to calculate y1 we can subtract it, so 2y1 is equal to 60 minus 15, that is 45. 45 by 2 is going to be 22.5. So the location of the first ball is going to be at 22.5 centimeter from this free surface downwards, and the location of the second ball is going to be 15 centimeter extra down, that is 37.5 centimeter. So these are our final answers. Okay, so these are our final answers. Thank you.